Welcome back to the part B of lecture 6. In this part, we are going to talk about feature selection, or also known as variable selection. Now, feature selection is typically a term which is more popular in the ML community or statistical machine learning community, and variable selection is a term which is more popular in the stat community, or typical statistics community. So but both of them are essentially the same thing they are doing. Suppose feature space has p many features, and these features could be original features or it could be engineered features. Anything can happen, and P is typically very large. P is typically very large. We would like to drop features which have no impact on the response. That is our target. So suppose y is the response variable. Y is the response variable, and x is the bunch of features or predictors. And out of P I want to select q many features. So P could be 2000. You can have a data set which has 2000 features, but I want to build a model out of 2000 features with only 15 features, 15 useful features, so that I can explain the model to the greater academic community, greater larger community. I can explain it to myself, I can explain it to my supervisor, I can explain it to my business, everybody has stake in this kind of model development. So the first thing I will talk about the best subset selection. To perform the best subset selection, we fit a separate least square regression best subset for each possible combinations of the P predictors. Okay, so what happens is this will fit all P models that contain exactly one predictors, then all PC2 models, all P combination 2 models, that is P into P minus 1 by 2 many models that contain exactly 2 predictors, and so forth. Then we look at all the resulting models with the goals that identifying the one is the best. Okay. Now the problem is the model space, that means the number of models that we have to fit is 2 to the P power P minus 1 many models. If I have P many features, so basically what is happening here, I have suppose y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Suppose I have a model with 3 predictors only. I have a data set which has only 3 predictors. Now how many ways we can fit the model? We can fit this way, or we can fit beta naught plus beta 1 x1. I can fit y equal to beta naught plus beta 2 x2. I can fit y3 equal to beta naught plus beta 3 x3. Then I can fit y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Then I can fit y equal to beta naught plus beta 1 x1 plus beta 3 x3 plus epsilon. Then I can fit y equal to beta naught plus beta 1 beta 2 x2 plus beta 3 x3 plus epsilon. So there are how many models? 1, 2, 3, 4, 5, 6, 7 many models. Now P is 3, so 2 to the power 3 is minus 1 is 7. So there are 7 many models. If there are 3 features, then 7 many models you can fit, and for each model you can calculate the RMSE and then see which model has the best least RMSE. That means that model has the best accuracy. You choose that model is your final model. So this is our target. Now what happens if you have 10 many features? Then you have to fit 2 to the power 10 minus 1 many models. So can you figure out what is that number? 2 to the power 10. Can you just use your calculator and figure out what is that number? Now how this typical best subset selection works? Let M naught denote the null model which contains no predictor, means y equal to beta naught plus epsilon. No more predictor is there. This is simply predict the sample mean of the observations. This is essentially the sample mean of the responses. Okay, beta naught is simply sample mean of the responses. Now you start with k equal to 1, k equal to 2, you write a for loop. Fit P, choose k many models that contain exactly k predictors. Then pick best among the PCK models, call it MK. Here best is defined as having smallest RSS or equivalent largest R square. And select single best model among the M0, M1, MP using the cross validation prediction error, AI's cross validated prediction error, AIC, BIC or adjusted R square. So this is what we typically do in doing best subset selection. Though the step 2 identifies the best model on training data of each subset, in order to reduce the problem from one of the 2 to the power p possible models to 1 p plus 1 possible models. The base subset selection involving fitting 2 to the power p models could be very difficult. Like if you choose p equal to 10, 20, the base subset selection requires fitting of 1,048,576 models, and it might take, just for p equal to 20 is very small data set. In today's world, p equal to 20 is a simple, very moderate size, like modest data set. You will not, any data set can have 20 features. Now if you do a best subset selection on that, then you have to fit 1 million model to get the best model out of it. So huge number of models that you have to fit. Then you have to, for each model you have to calculate R square or root mean square error, and then you have to, based on that, you have to select which model you want to choose your best model. So this means that best subset selection is almost not possible unless it's a toy data set or a small data set. So that creates a problem for us. So that is where the forward stepwise selection comes in handy. So what forward stepwise selection does, it starts with the M0 denote the null model which contains no predictors, and consider p minus k models that then loop starts k equal to 0, 1, 2 up to p minus 1, and consider p minus 1 models that augment the predictors in MK with one additional predictor. So if you are at a kth step, you already have chosen x1 to xk, it will keep all these k models and then it will just try rest of the features which have not tried. These features will be add here and check if the residual sum of square is being minimized or not, and then rest of the thing is exactly same as the best subset selection. If it does that, unlike best subset selection, which involve fitting of 2 to the power p many models, forward stepwise selection involves fitting of null model along with p minus k many models in the kth iteration. So the amount of total model that you have to fit is p into p plus 1 by 2 plus 1, the one null model. So if you have p equal to 20, best subset selection, you have to fit 1,048,576 model, whereas in forward stepwise selection, it is required to fit only 211 models. So the huge improvement. It's a huge improvement if you do forward stepwise selection. In terms of time complexity, it's a huge improvement if you do stepwise selection and not the best subset selection. So forward stepwise selection can be applied even in the high dimensional data setting where n is less than p. In this case, it is possible to construct submodels up to n minus 1 only. Okay. So it is doable even in the high dimension problem. Then another algorithm is backward stepwise selection. So how it does? So it starts slightly opposite way, instead of forward stepwise selection. So it starts with MP, which denote the full model. Okay, so it will first fit beta naught plus beta 1 x1 plus dot 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 beta p xp plus epsilon. So it will first fit a model with all features. Then it will start dropping the features. First, so that's why it's running the loop from p to p minus 1 to dot 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 up to 1. So consider all k models that contain all but 1 predictors in mk for total k minus 1 predictors. And then rest of the thing will be as exactly same as the previous algorithm. So like forward stepwise, the backward stepwise also approach the searches through only 1 plus p into p plus 1 by 2 models. So it can be applied in setting where p is too many large, apply base subset selection. So also like forward stepwise selection, the backward stepwise selection is not guaranteed to yield the best model. It is not guaranteed to yield the best model containing the subset of p predictors. It can miss the best model as well, because you are making some assumption, you are making some approximations now. Okay. Now implementation. How can you implement this thing? In R, built-in function called step in stats package is there. You just have to mention that select model by AIC in stepwise algorithm. You have to just say forward, backward, or both, and it will just do the stepwise selection for you. And several Python implementation of stepwise feature selection is also available, so you don't have to worry about that. So in the next video, we will discuss the issues of multicollinearity and so on. Thank you so much. See you in the next video.